Hey, ooey, it's
Hi,
dark.
everybody.
Hi.
Very dark for you.
Yeah, but I think if I turn on the light in the back of me, it will be, I will be
Sure,
Lit.
outshonen. I don't know what the word is.
in the shadows.
Yeah.
I'll be
Hi.
eating my lunch, guys.
Allison, just a short organizational question. Will you start with your part, sharing your screen, and then we'll switch, or?
Yeah, that works for me. I kind of have an overview and then a couple of questions. And then we can just kind of go straight into yours and then leave most of the time open for discussion.
Mhm.
That works.
We have a unicorn joining us today.
Oh. Do we have 3 wishes for free if a unicorn joins, or? Like world peace and gummy bears and I don't know the third.
Holiday on a tropical island.
Oh yeah.
Good one.
Oh no, end of COVID. How is that?
Oh yeah, that'd be a good one.
Yeah, because we can't even go to a tropical island now, so we have to have that first. First things first.
A tropical island with magical COVID-free properties. It's a unicorn after all. Zona started horse riding lessons.
Oh, cool.
Oh.
Sounds kind of scary.
Yeah, I think I've ridden on a horse once ever. She'll be really good at it.
Oh yeah.
So was it a horse or a unicorn?
Nice.
Oh boy.
Okay. Yeah, that's a good first step to learn to ride a unicorn. Start with horses. Actually, unicorns are easier because you can hold on to the horn. Huh?
If that's okay, we can wait for a couple more minutes and we can get it started.
You know, since the first time that I was an hour late, I'm now every Wednesday when we have the meeting, I look on several hours, testing if there's a connection because I'm not completely sure what the correct time is. It's really ridiculous, but that's just like it is.
Yeah, and it changed, right? Because like I'm glad that I looked at my calendar this morning because I thought it was at noon my time, and then I saw that it was actually at 11, so I just logged on now.
It's a moving target, yes.
And I think it's Arizona's fault. Like I'm blaming it on Arizona for some reason because they have a different times change than
no, because
the rest of the country.
We're the sensible ones who never change time zones.
Yeah, but you can't convince the rest of the country to do that, so we're all we're all confused about you.
There's actually an article in Scientific American, I think, talking about how many countries are considering not doing daylight savings time anymore because a lot of doctors are writing opinions saying that it's bad for health due to the change of people's circadian rhythms.
And actually, it's now proven that you don't actually save daylight, right? It's exactly the same amount.
Well, I would prefer if it was just daylight savings all the time instead of standard time all the time. So if they do go for one, I'd prefer it to stay later into the day or stay lighter.
I see what just a consistent one. Yeah.
Although I guess I could just get up earlier, but I don't want to do that.
After years of struggling with the time zone change thing, I finally discovered an app for Mac people called Clocker, which you can install on your computer. And it's just a little thing you just, on your top bar, you click on it, it comes down and it shows you the time in every time zone and it updates accordingly. So you don't have to do any calculations anymore.
Yeah, I just Google what time is it right now in wherever I'm interested in looking at.
Yeah, but it sort of takes, I got tired of doing that because it takes so much effort. And then you got to, you know, this puts it all in one place. I see somebody's screen. Allison's.
Oh, that should be mine, right? Hopefully it's a slideshow for whenever we want to get started.
Yeah, I think it's a good time to get started, Allison. So
Yep,
go
that's
ahead.
working.
All right, cool. Hello, everybody. Welcome to the 3rd or 4th edition of our IT reading group. Today, Uwe and I are going to moderate on another one of the information theory WRR debate series papers. So our very first meeting, we talked about kind of the overall overview of all of these debate papers. But this one will be focusing specifically on Stephen and Ben's paper that's focusing on sharper predictions using Occam's digital razor. So first I'll just provide, whoop, my slides aren't going anywhere. Huh. I wonder, maybe if I stop share and share screen. Sometimes it's a Zoom thing. Nope.
You need to have your mouse.
Oh, there we go. Okay, I had to like click on the slide and not use the mouse. So first of all, I'll go through a pretty brief, less than 10-minute background and bring up a few thoughts and questions, and then Uwe has some follow-up questions, probably at a lot deeper level that he's been involved in with these sorts of questions, and hopefully we'll leave most of the rest of the time open for kind of free-flowing discussion. So I'll start with some background on Occam's razor. It's also called the law of parsimony. And being a modeling novice, I had to look up basically the dictionary definition of parsimony. And the definition that made the most sense to me was based on its Latin root, which means to be sparing, which totally made sense once, you know, I kind of equated that with the different ways of stating Occam's razor. So basically, Occam's razor is the idea that, and this can be stated in a whole lot of different ways, so I've listed a few of them here. And basically, it's no more assumptions should be made than are necessary, or that the simplest explanation that still accounts for all the facts of interest is probably the right one. In the modeling context that we're kind of talking about it today, it's basically the simplest model at a given performance level is going to be the preferable model. So if we have a range of models and they all provide the same level of performance, we should select the simplest one as the most likely explanation. And finally, the quote that everything should be made as simple as possible, but not simpler. So you get the general idea that it's kind of just saying, you know, simpler is better. So in this paper, we're thinking about modeling in terms of data compression, where data compression is defined by, or where complexity is defined by description lengths. So we're looking at our model complexity or our data complexity in terms of how many bits does it take to completely describe them. And algorithmic information theory measures can give us a sort of a quantitative or potentially quantitative way to pick the simplest model for a given performance level. So to actually apply Occam's razor given a range of models. Oop. So some background on algorithmic information theory. I actually didn't get as much of a chance as I wanted to this past couple weeks. I'm going to blame that on daylight savings time, actually, in the last couple of weeks to read up on this as much as I wanted to. But basically, it's based on several kind of independently distributed papers in the 1960s And it's related to creating algorithms to reproduce data and looking for the shortest way to describe data. So what I think about immediately when we think about this is probably all of our compression algorithms and then different ways that we can compress our data sets using, zip files and different sorts of compression mechanisms. And this is not exactly the reason it's different between the reason that algorithmic IT and Shannon information theory are different is because AIT is actually, I think about it as more of on the practical side of actually compressing the data, while Shannon IT is kind of looking at measures like entropy in terms of sort of like a bulk, which gives you some boundaries, but is not actually performing this compression. So for example, if I have a binary sequence of a ton of zeros and ones, I could have a bunch of cases where my entropy is always 1. So I could have maximal uncertainty, but I could have cases where, one case might be 0, 0, 1 repeated 100 times, and another case could be completely random, or 0, 1, 1, 0, I guess, for your entropy to be 1. And with information theory, we could say things like, this is the entropy. We could say things like, this is the lagged mutual information between past values and current values. So you could give an idea of the compressibility of your data sequence based on how much information past values can provide you about future values. But algorithmic information theory would actually allow you to perform that compression and be able to say, well, this series is just, 100 repetitions of 0, 1, 1, 0. So AIT is based on a minimum description length. So for any given series, you should have some, unachievable minimum description length that you could compress your data down to. And unfortunately, this is actually incomputable. So I'll talk a little bit more about that in a minute. However, these data compression algorithms provide a substitute estimate of compressibility. So these algorithms can kind of give you close to optimal compression of your data sets. So the example, or one hypothetical example provided in the paper, sorry, I have to move my picture is in the way of my slides. Okay, so an example from the paper is basically say we have a rainfall and a runoff time series. We could store rainfall along with a perfect runoff model that perfectly reproduces our runoff. And then we wouldn't have to store both R and Q. So theoretically, we could save a lot of space by storing one variable. So we could store our input variable and then store a perfect model that then we can use the model to get Q back. However, we probably don't, or we almost certainly don't have a perfect model for Q, but what we do have is a lossy model. So, oops, slide problems. So to introduce some terms to this, we're looking at L as kind of a description length. So L of M means the description length of that lossy model that we have. L of D given M is the description of the file that makes up for your lossiness of your model. So this would be the missing information that you need to perfectly correct your model. So given that our model has some error associated with it, this would basically be the model and all the residuals, for example. So it'd be, this is what you need to make your, to perfectly recreate your data set. And finally, the total length that we're looking at is the addition of these two terms. So this is the lossless description length of the data when we're using the model. So hopefully these two things together save you some space relative to if you had just stored your complete set of input and observed data sets. So here is a plot from the paper, and these are just examples. As far as I can tell, these are sort of just hypothetical examples of some different models. And here we're plotting on the x-axis this lossless description length. So this LDM is made up of two components, and that's the description length of the model itself, and then the remaining kind of missing information description length. So we have some examples. So for example, the original data itself, if we just stored everything, this is just one component, and it's basically just the size of the data, right? And then we have other cases where we have, for example, we have a really complex model that does explain everything, but it's a really large model, so our model size is very large. And then we have other cases where, you know, we have less complex models, but then we have some missing information that we need to add in to completely explain our original data. So here would be our optimal case. So we want to minimize our total lossless size. So we have a model and it has some residuals, but compared to all these other models, it can be compressed to a larger degree. And this value here is kind of an optimal, kind of the optimal compression that we could hope to achieve. So this would be the size of the very smallest program or model that can reproduce the data. However, this is not computable, but they make sure to mention in the paper that this is not our fault. This is a property of algorithmic information theory that we actually can never find out what this Kolmogorov complexity is. So back to kind of looking at these hypothetical models. This is another plot from the paper. Basically, we can plot models in terms of their model complexity. So their the complexity, size of the model on the x-axis, and we can plot this other term, so this L missing information on the other axis, and both of these together make up that total total lossless size. And Occam's razor basically tells us that if we draw a line here, or if we draw like a horizontal line, for example, so we have the same performance level, the simpler model is better, right? So if we have the same model information loss, which with a large range of complexities, we kind of want to move this way to go for simpler models. However, we could also look at this vertically and say, well, for a given constant model complexity, we would like to get better performance. So a more strong version of parsimony than just applying Occam's razor, which only would allow us to theoretically compare models that are the same size. We actually kind of want to go this direction to both obtain simpler models with better performance. And here is this incomputable sort of limit that we actually don't know what it is, but we can approach it with our simplest models that have the best performance. Right, so that was a pretty brief overview. These are just a couple initial questions or thoughts that range from very kind of like technical to potentially a little bit more philosophical. So I can just go through these and then we can either talk about them briefly now or just kind of lump them in with some of Uwe's presentations. So the first thing I wondered was, are there a lot of examples of practical applications of this? And say I have a model, how can I actually estimate my complexity? And the first thing I think of is, well, what if I just tried to compress it using one of these compression algorithms? And you know, that seems to be the way that you would address how complex your model is. But then I thought about how bad code I've seen in my lifetime and how I've written some really bad code in my lifetime. And does this assume that our model is expertly coded? So for example, what if I have a really simple model, but I wrote it in a really complicated manner? Would that make my model seem more complex? That's just kind of a technical question. And more on the general side of the idea of Occam's razor, something that I thought about. So if you apply Occam's razor, you would say, you know, we should get rid of the complex model or not choose the complex model if the simple model performs the same or better. But given that we know the world is complex, does that really just mean that basically we do need a complex model, but we just don't have the right complex model, and that we need to keep working on it or keep building on it to achieve better performance, which doesn't necessarily mean that, you know, we're not applying Occam's razor, but it's just kind of a different way of looking at it, as, you know, if our simpler model performs better, that just means that, you know, there's some flaw in our complex model, but theoretically a complex model should better reflect the real world. So this kind of makes me think of things like chaos theory and how, you know, initial conditions can lead to really unpredictable outcomes, and that type of thing. So I kind of wonder where the merger is between those ideas. And finally, I thought about models' motivations. So models can have different, you might use the same model for different things, right? So, and I think it's mentioned in the paper that, you know, this sort of depends on what you're looking for out of your model. So for example, you might get a really good runoff prediction from a really simple rainfall runoff model, but a more complicated model that doesn't do quite as well predicting runoff might provide you an estimate of a bunch of other variables that you're also interested in. So I was kind of thinking that these components, you sort of have to agree upon from the beginning, what are we looking for? You know, like what are the outcome variables that we're most interested in, and do they all have the same relevance or importance to our intended use? So for a different person, they might make a different decision of which model is the chosen one, depending on what of all the output variables are the ones that they're interested in. So that's all I have. So we can switch over to and then open it up. I think you're on mute, Uwe.
Okay, unmuted. I hate it when I only have one screen and things start stockpiling, but that's just what happens. So I think I'll briefly go through my comments, and then we can select, or Stephen can select in which way he wants to address these questions. And obviously also what other questions emerge. So I think for general questions, but first a comment. What I really like about this paper is the fundamental way in which model building and the definition of what a good model is addressed, which is, and that's also what Stephen and Ben mentioned in the paper, which is completely independent of, say, the modeling approach. And this will really help to bridge a gap of comparability among models. So if this really works in practice, I think it will be a wonderful approach for a really rigorous way of gaining knowledge defining what knowledge is and on model building. So I really enjoyed reading this paper a lot. So here are some questions. Some of them Stephen may already be familiar with. The first relates to this really interesting statement that was developed by Solomonov, which is mentioned in the paper. This description length of the model has been shown to relate to the prior probability of the model, meaning in very brief that shorter models have a higher probability of being good models, and that is before seeing the data. And this is really fascinating. I haven't read the Solomonov paper, and the question would be, is there a way to very briefly prove this or describe this? And what I was also wondering is, isn't this description length of the model a posterior and not a prior, the description length of the model, isn't that after the model has seen the data, meaning that the model has been tuned or calibrated or been exposed to the data? So isn't then LM the posterior probability with respect to the learning data? And if we think of another data set, one that we would try to predict, an out of sample data set, does this Solomonov relation still hold for the unseen data if the unseen data are not consistent with the learning situation? So I'm not completely clear of what D is. Is it the learning data or the unseen data that are yet to come? The next question.
Uwe,
sorry?
If I could just add to that, is the question of what is meant by good in this case. Yeah. When you say shorter models are more, the probability of shorter models being good models is higher, is what you said. Just the ambiguity about what we mean by good. Yeah.
Okay, the next question I have is, in the paper, I know this is for demonstration purposes, but nevertheless, the authors talk about two things. There is basically the model that is the expression of the patterns we have captured in the data. And then we have basically a noise term or an unexplained term, this description length of the data given the model to capture that information loss. And along the lines of what we talked about in the last reading group, when Hoshin was talking about the say sequential move in neural networks from an input to an output, is it also imaginable that we have more than these two layers or elements? So we have a soft transition from, say, patterns captured to noise taken care of. And are there strategies to choose then the best number of such layers? And also related to that, because now we would have something like, hard knowledge, softer knowledge, which is maybe a transition from case-specific to universal knowledge in such a description. In the same way as the authors suggest in the paper, that we could use generally available knowledge expressed by code libraries and not count that in the bit counts. Could we also think of counting these partly or not, expressing that it's generally available knowledge or more case-specific knowledge? So this is the second question. The third, and Stephen will hate me for that maybe, is because we've been discussing this for a long time. In this entire paper, there's no talk of computational complexity, meaning the effort that this universal computer needs to generate from this minimally adequate program, the actual sequence of data to do the prediction. This effort is not counted. So what we see here underlain by this yellow cloud is the two aspects of models that Stephen and Ben talk about. It's performance of a model, which can be measured by the information loss of the model or the information still missing, and its descriptive complexity, which is this size of the model, yeah, L of M. And what we don't talk about is computational complexity, meaning the effort, the bits that need to be manipulated to let the code seed unfold into the blossom of the data. So this is my question: should we add computational complexity to this business or not? And then a few practical considerations. I would like to see or hear how in this business of transforming data to a model and the data loss that we have to make up, how can we avoid lossless inflation here? It would seem to me, by the models that we built, this description length of the model and the description length of the data given the model is maybe larger, much larger than the description length of the original data. Then the second practical question, do you have an idea of the order of magnitude of these two components, information loss and description length? So is it as a objective function helpful to add them together to a single unit, or should we rather treat these two, because there may be orders of magnitude apart, should we treat them in a Pareto style optimization as two separate objectives? Then another question that Ben and Stephen also mentioned in the paper, where should we start and end the bit counting? So are, for example, input data part of the model or not? You know, it's always imaginable that a lot of information is stored in forcing data and not in the model. Then we would miss something. And I don't know if there are general guidelines for this. And the last question is, let's suppose we arrive in the situation that we have models that are identical with respect to the sum of this descriptive complexity and the loss, the information loss. Let's say they are identical, the sum, but these two terms are not the same. Which would be a good strategy to choose then a parsimonious model? The minimum description length model, or maybe something else? So that's all I have for now.
Hojin?
Since it was the most recent point that we brought up, I thought I would start by weighing in on that one. So there's the overlap between these notions of parsimony, simplicity, the notion of descriptive complexity, and we just brought up the notion of computational complexity. And I'll save the description of parsimony for later, the discussion of parsimony for later. But having heard Uwe's argument now and actually before, I tend to think that computational complexity is actually the more important issue, an issue that overrides descriptive complexity. And I'm thinking of computational complexity as the number of operations that I need to perform in order to transform from X to Y, if X is the inputs and Y is the outputs. And in this regard, I don't think descriptive complexity is particularly important, because I could use a very complicated description to perform the same number of operations, or I could provide a very simple description to perform the same number of operations. And probably the only difference would be this concept of that scientists and physicists call beauty, that something is more beautiful because it can be explained more with a smaller number of bits. So from a functional point of view, it seems to me computational complexity is more important. But then if I had two models with comparable or identical computational complexity, I might prefer the simpler descriptive complexity one.
Yeah, I think I disagree with that. So for descriptive complexity, there is this how do you say it? This equivalence that no matter what language you use, there's an additive constant difference at most. So that seems to indicate something really fundamental, that some things are complex, some things are simple, and the particular language you choose doesn't matter except for this additive constant, which can be still huge if you look at the size of data sets we normally have access to. Well, for computational complexity, there is not such a similar thing. So I tend to think of computational complexity as something not really linked to learning that much, except in practical ways and in fundamental ways, like are you really explaining something that is more linked to how short you can describe it. I must say I haven't slept very well, so I'm not sure if I'm at my best at explaining things today. Let's see. Yeah, so one way to think about it is that if you imagine this Turing machine, so it's a thing that you feed with a tape, that's the program, and then it moves the tape around, reads and writes symbols. So the computational complexity would be the number of steps until it holds, and the descriptive complexity would be the length of bits on the input tape that it reads. So one way to think about why simple programs are linked to higher prior probability is that if you look at self-delimiting Turing machines, which are defined that if you feed them the tape, they perform their steps and they have one certain hold state that indicates that they're finished with the program. And no matter what you put on the tape, you only count the symbols that it actually read until it holds, because anything else on the tape is gibberish, like it's in our DNA, it's the junk DNA that's not read. Yeah, you have to ask mommy. Okay.
Is that the reason you didn't sleep?
Yeah, not so much actually.
Okay.
We're both having meetings, my wife and I, and it's a holiday. It's Remembrance Day, so the kids are home. No, just a sec. Yeah, so basically the only part that it reads is actually called the program then. So if you look at how many of such programs there are, it's 2 to the power of minus the length, because it's just the number of combinations of ones and zeros you can make of that length. And that chunk of the program stands for any extension of that program, because if you pad zeros and ones after it, you can, it's essentially the same program because it only reads that part. So that's where the relation between Ruben, you have to, okay, you can say hi. Yeah. Okay, maybe I'll take a brief break to switch on a video for them, and then I'll come back. That's probably more efficient.
Okay. I'm going to wait for Stephen to come back to continue that, because I've got some counter statements or objections. But maybe we could take other thoughts or comments in the meantime.
Maybe I'll hazard a question. My name is Dan. I'm one of Stephen's students. And I guess I'm having trouble making the link between the practical and the general case that he's describing. I guess I'm thinking of the way that I'm writing my code, which is tending, I guess, ideally towards more readable but more concise statements that perform better. But you know, learning about new libraries, say, that are enabled with, like, I'm thinking of just-in-time compilers. So I'm having to rewrite functions in much more verbose ways. So the description length of the code itself would be much, much longer, but for, you know, 4 or 5 orders of magnitude better computational performance. So that, I mean, that's something that I think is practically very important. But of course, I guess at the lower machine language, I don't know what the difference is, because I don't know linear B, I don't know any of those things. So, but I think that you know, 4 or 5 orders of magnitude difference certainly is, I mean, critical. I think it's critical, because how do you evaluate more models? How do you iterate through and you know, traverse that decision space? So.
Go ahead, Hoshi.
Okay, since Stephen's back. So this is a kind of objection to you, Stephen, maybe not, because I think we're converging on something. So you mentioned the issue of overhead, yeah? And in that context, let me see if I can explain this well. I'm reminded of Gödel's theorem, which I interpreted, there may be different ways of interpreting, but I interpret it as there is no formal system that, he was talking about mathematics, that can reach all spaces. In other words, there are unreachable spaces, spaces that are unreachable using any formal framework, right? And what this reminds me of is the inherent limitation of any representational framework that we choose. Any framework that we use to describe reality, by its very nature, limits the questions that you can ask and the answers that you can receive. So what this says to me is that all representations presume some kind of representational framework, and that representational framework is the overhead that you're talking about. And it could be descriptive overhead, it could be computational methods overhead, things that you have to have, without which you can't do anything, which for us is things like operations like addition, multiplication, log transforms, exponentiation, all the things that we presume as being the foundations of our computational framework, including the binary representation and so on. This causes me to speculate that the representation that we choose could in practice bias the representation of optimality. And it's very hard to know in that context then. So if you choose one representational framework, let's say an alien race on a different planet evolves a different representational framework, they might, and they're comparing a set of models, they might choose one in that representational framework, whereas if you went to a different one, you might choose a different one. It's just a speculation. But this is why, so what I meant to say by this is that I think we have to presume a representational framework in any discussion that we have. We have to use the same representational framework to compare all of our models and methods. And then we have to accept that whatever optimality result we arrive at is true in the context of that framework. And then I get to the point of whether there's a distinct difference between descriptive complexity and computational complexity.
Yeah, so two things, like I think the Church-Turing thesis says that in principle anything that's computable can be computed by a Turing machine, so a universal Turing machine. So maybe Gödel puts a limit on what can be proven, but it doesn't really say that there's things you cannot represent in terms of a Turing machine.
It's a thesis, not a proof. Yeah.
Yeah, which in itself is probably a result of Gödel. That and actually there's interpretations of the halting problem as another way to state Turing's incompleteness theorem. Like Gregory Chaitin is writing whole books about that. Like I think the probability that a Turing machine will halt, it's some incomputable number, and that's infinitely long, and that's the reason why, like, if you would be able to determine all the digits of that probability, then you would have invalidated Turing's incompleteness theorem. So he sees all the bits in this number, what he calls omega, as all the fundamental truths in mathematics that kind of go on infinitely. I agree with your point about that the representation might bias us. So that's the point where this additive constant comes in. So this theory says that some things are complex, some things are less complex, but what you find complex in one language might be simple in another, but only up to an additive constant. So if there's a process generating data, then eventually, if you have enough data, you will converge whatever language you have to one process being complex and one being simple. But in the view of limited data, this additive constant actually can completely flip your results. So yeah, definitely, I think Allison mentioned she saw it more as a practical approach, but I think that's a bit of an idle hope. So the compression approach is a kind of a simplification of making things practical, but that doesn't capture the full power of the theory. So because it's so fundamental, basically there's no, it keeps all the nastiness of all the big philosophical problems. You cannot shove them under the carpet because it's so fundamental. So you're not going to find any practical way to apply this, but you can maybe see it as a thing to think about when you look at practical approaches and see what simplifications they make to get around some of the fundamental problems in learning.
Stephen?
Yeah.
Stephen? Does Turing make any statement about, you know, the effort it takes to produce the output? I mean, I would assume I have learned something about the system I'm representing if I have two pieces of code that are exactly the same length, but one takes a year and the other takes a minute to produce exactly the same output, then I'd say I have learned more about the system I'm representing if I build a machine that does the same in a shorter number of operations. Did Turing refer to that somehow?
I don't think so, at least not in his work. So maybe take pi as an example. so do we think the number pi is something simple or complex? So if you want to compute pi, you can go on infinitely, but the process to do it, like there's several ways in which you can write a short computer program that, if you run it long enough, produce an arbitrary number of digits. So so that's one example where maybe to reflect upon whether you think computational complexity is fundamental. The other one is quantum computation, maybe, that there is a shift in computational complexity classes if you move from a classical computer to a quantum computer, and that's not by an additive constant. It's really that things that are exponential in one become polynomial in another. So there the switch of computer does make a fundamental difference in what the computational complexity is. So to me that indicates that maybe, well, I think computational complexity is probably fundamental in a lot of ways as well, but I think not in this concept of learning. I think it's important from a practical perspective, but not on really the question like, have you explained something? Like, do you explain the ratio between the radius and the circumference of a circle? In terms of computational complexity, you could never explain that because there's not a simple way to express that ratio. But still, pi is a very fundamental constant that pops up in many different ways. And you can describe it in many different short ways, but none of them is like computationally efficient. So yeah, so in any practical application, since you have this incomputability, there is an important role for computational complexity, because we have to make some approximation that's computable. So there you might eventually want to trade off some of your, if you have to, you can never learn every pattern. Like there might be certain patterns that are there, but you cannot learn because finding the shortest program takes forever. Okay, I'll shut up for a while.
Allison, can I take this in a slightly different direction?
Oh yeah, sure. Go ahead. I was just gonna say with the practical side, it's not the incomputability of a limit that bothers me from the practical side. I guess it's just the potential inability to even compare two models. So, you know, I'm not even sure how to compare two models that we do have.
Yeah.
Based on this concept, you know, it's like you have to agree upon some terms first.
And I think that might be related to this additive constant, which in our typical realm of how much data we have still plays a big role. The other thing is that we typically think of our variables as coming from some real numbered values. So actually the precision that we think about is infinite. So then any description of the data will be infinite as well. So even if you compress by a certain amount, things still look infinite. So you have to make some discretization first. So this theory comes from computer science, in which things are already discrete. So then you don't have this, like if I have to if you have a random number generator and I have to guess what it is, what the next sequence is, then this applies very well, because you have a limited length program producing stuff. I can enumerate over all programs and look at the data you produced, see which ones fit, prefer the simplest, and as more data comes in, I might switch to a more complex model. And that actually relates to a question you asked in the beginning about Occam's razor, like, should you just throw away the too complex model even if you know that the reality is complex? And the answer to that is that in the end, what we calculate would be a posterior probability of the model. So there's some prior probability that's a function of the complexity, and then there's the fit to data. But all other models that we consider also still have probabilities. They're just lower. So as soon as more data comes in, so there's a second principle called, it's like Epicurus principle of multiple working hypothesis. So that basically says that you apply Occam's razor, but instead of just comparing models and throwing one away, you just compare them, assign probabilities. And then if more data comes in, you do it again and the probabilities will shift a bit. So the prior probabilities stay the same, but at a certain point, maybe your complex model overtakes the simpler model. But in the end, you can only make decisions on the data you have, right? So if you're saying, I know that reality is more complex, you're actually cheating because your model doesn't know that, because you just feed it to data. So actually, if you would feed it to data that shows that reality is more complex, maybe it wouldn't prefer that simpler model.
Yeah, that's actually where I wanted to go, which is, you know, you have the whole, I don't know if he actually said it or not, but Einstein's reputative said you make things as simple as possible, but not simpler. And when you said, Allison, that you know reality is more complex, so why should I prefer a model that's simpler than my knowledge? My interpretation of that is the statement, I know reality is more complex, is a prior on that model, or should be stated as a prior on that model. And as Stephen pointed out, that's based on a lot of other information that's not necessarily contained in the current data set that we're then using to interpret the model. So I've never been one to blindly agree with the idea that you choose the most simple explanation, because I find an interesting opposition between the notion of simplicity and flexibility for learning. In other words, I could build a model that is simple but makes it hard for me to learn. And I would probably, be given my own bias, choose a model that allows me to learn, is more flexible, has more potential for learning in it from new data. But that goes back to the issue of representation. Does your representation make it very, very difficult to generalize your model or not?
And I guess in the algorithmic information theory framework, the learning consists of keeping this flock of several models, and you're constantly assessing based on how well they compress which one does best, but you never throw it. So there's this Solomonov induction. That's basically, I didn't talk about it in the paper, but that's basically taking this approach and then adding that you keep all models and then make your final prediction is just a mixture of what all the models predict weighted by probability. And that's what they say is the ultimate way to learn, because your model space is basically anything computable. You have a way to put a prior on everything, which is the complexity, and you just apply Bayes' rule to learn from new data. So that will converge. Eventually, it will always converge, and it will converge fastest for any for the general set of all processes. Of course, for specific ones, there could be things that converge faster, but if you have no idea what generated your data except it's a computable process, then that is the fastest way to converge, which is pretty disappointingly slow.
But is the reduction to a single dimension of bit length an oversimplification? Is kind of my question.
Not in the way to, yeah, so in your case, you're saying I want to have my one model be a good learner. So in that case, I agree that more flexibility and over complexity maybe is a good guarantee forward to keep absorbing new information. But if you keep a flock of models, then it doesn't matter to have this super sheep that can be anything. As long as you have enough diversity in your team, you can always switch your preferred sheep in the flock. Sorry.
Which means you need to add that flock of models, all the representations to your overhead.
Okay, yeah, so that's a good point. Like, do you... So I think what I described in the paper is just a way to assess whether one given model is preferred over another one. So you, and that's all it is. So, and it's not even like saying this one is wrong, this one is right, but in the end, if a model is one bit longer in total description length, so the model plus the data, then it's twice as unlikely in principle, because it's 2 to the...
Can I ask a question? Maybe it's a bit tangential. If we look at the history of science, progress has been made to some extent by theories and models that predict what we observe. But a lot of progress has been made by understanding the errors that of what is not being predicted, right? So the difference between what data says and the model says. Examples are many, and as a result of this, slowly but surely, the complexity of the model has been increasing because the need for what we want to predict, the need for the interdependencies that are deeply embedded in our natural systems that inform the outcomes have to somehow make it into the models. A simple example is when first we started developing climate models in the 70s and the 80s. Their predictions were way off because cloud processes were not incorporated very well. And when they started putting in cloud processes, that prediction started to improve, right? There are many such examples. So where in this algorithmic information theory is there a mechanism for us to understand the lack of prediction or the errors that arise between model prediction and data? And how does that inform the learning? And in this case, learning is not better parameterization of the model, but better informed components. So new processes may come into play, which are not in the models. And of necessity, that is going to increase the complexity of the model, not necessarily simplify. So how do we reconcile that? I think that's something I'm not able to get my arms around.
Yeah, so let's suppose there. So first of all, this this framework is pretty dumb, right? It just measures the lengths and then says which one is preferred, how much probability. So, and it only operates on data, not on reality. So as soon as we do these very precise experiments and we have data that shows that our predictions are imperfect, you will see that to losslessly compress them, we have our old like Newtonian model, and then we still need some description length as a way to fudge the predictions to reality. So basically you store the errors, and that if you have enough observations that consistently show errors, you see that that model becomes quite long. Now, if there's some kind of pattern, not only in the errors, but actually if you relook at the whole data set and are able to find a different pattern than the part of your model that you had before that doesn't have those errors, then suddenly you'll find that that's more a shorter description than your original model plus the errors. So actually in algorithmic information theory, there's no real distinction between what we call the model part and the errors. So the way we presented it in the paper, like you have the model and the description of the data given the model, that's split into two parts. It's mostly to make it relatable to the way we humans think about things as being pattern versus noise. But actually in reality, of course, everything is pattern. And what we call noise is just a part of the pattern that we haven't seen yet. So in the end, you're just looking for one algorithm that describes anything, and probably it will look like something where a part is a description of the pattern and a part is the noise. But in principle, that's not really necessary.
Okay. Yeah, Hoshin?
Praveen, your comment sparked a question for me, which is, I think what you were talking about is when you add more degrees of freedom or more variables in the data, effectively. You observe more aspects of reality. So I'm wondering whether this discussion of complexity is something related to complexity of the model representation relative to the implicit complexity embodied in the data. In other words, as we add more degrees of freedom, we would necessarily increase absolute complexity, but hopefully not ultimately relative complexity in some sense.
Yeah, no, I mean, so, I mean, you're trying to put some bounds on this, right? I mean, basically, when we think about natural systems, I mean, we're always, the way we think about it in hydrology is there are initial conditions and boundary conditions. And that basically provides a context in which the system is evolving, right? That set of boundary conditions that you choose is then essentially enabler of the degrees of freedom. You cannot have a degree of freedom that is not constrained by a boundary condition if that's important, right? So implicitly we're putting in there, and that's the reason why I chose the example of the climate model, because essentially the only boundary condition is your solar radiation in theory, right? I mean, the rest of it is internal to the system, depending on how detailed you want to characterize it in there. And so the data that you would observe is again related to the context. So as you expand the context, your ability to predict will increase because you're incorporating more dependencies in there. The boundary conditions essentially constrain the dependencies in there. So that is the key. So I think the question was, is this a conditional learning where basically we say, here are n degrees of freedom and what is the best model that we can learn through this. Even though, for example, you might be interested in a set of predictions like temperature and flow, for example, right? Or is it an unconstrained learning, in which case anything and everything that might be relevant to this. So for example, would the solar cycles be relevant to temperature variation, right? I think it's probably useful to cast it in specific context. I struggle with this concept. I mean, I appreciate the value of this concept, but I struggle with it for lack of examples, and I haven't seen those. I mean, it's still very abstract. And if we had specific examples, specific mathematical infrastructure, which lays out the assumptions and the constraints under which these things work, it would probably be useful to make advances. So I wonder if that is something that could be done.
If I could talk in between Stephen's example and yours. Let's say I have streamflow and I have, in reality, 3 variables: precipitation, temperature, and wind speed, which together might make a perfect forecast of streamflow. But I happen to have not observed wind speed. So then I could generate a model with precipitation and temperature, which predicts streamflow, and the residuals of that model would have to be added together to the description length, per Stephen's example.
Yeah.
But let's now assume that those residuals correlate perfectly, perfect mutual information with wind speed, and I could describe wind speed by a very simple 1 or 2 parameter model. That seems to me to fall in this category of something you were describing as you don't have enough. It starts to feel a little bit like what's his name's description of entropy as being missing or hidden information. It's the information that we lack. In other words, it appears to be noise, but it's not necessarily noise. It's just because we haven't observed something important.
Right.
I have a question. Maybe it's a bit philosophical, but so I am struggling now. For example, would we like, or would we prefer to include all possible processes? So this increases model complexity, but because we cannot reconcile with the available data, we could not infer these processes, or we could like to still keep the concept of parsimony, but this, of course, writes out of having the right answers, because we are not including some processes. So I don't know. Is parsimony, let's say, good in some point of view, but in other ones you find that if you want to include more processes and you want to include to learn more, you cannot. You should include more processes actually, right? But you don't have the data, so I would like to know a bit more. I mean, this is I know it's quite fundamental, right, and philosophical, but
well,
kind of struggling.
I think this algorithmic information theory and this Solomonov induction is like the ultimate way to learn in a vacuum of where you don't have any prior knowledge. You just have data and you're trying to figure out what computable process generated it. But of course, that's very different from the situation in hydrology, where for any given data set, that we are typically using in model inference, there's a lot of things we do know about reality that are not in the data set per se. So the fact that we know there's processes that maybe you don't see in the limited data you have, or you cannot really discern from the data. Maybe we've seen that in other catchments or in a laboratory. So that's where it gets interesting, and also one of the impediments of using this in a practical way in hydrology is that we always have this big prior knowledge. So in that case, the prior knowledge actually acts as the data that we are trying to compress, maybe. So instead of counting it as extra complexity, if we put physics in our models, we are just saying, well, these are given, so it's not something I'm inferring from my data set. They're just facts that I add. And in that case, they're not really part of the description of the data set. They're just independent truths. So the idea that Occam's razor wants to throw away complications, but that's complications of the explanation. But in this case, those complications are not part of your explanation. They're kind of independent truths that you derived from, that were used to explain something else before, right? So in that sense, that's why.
Yeah, because of the other part takes care about the evidence. Right?
Yeah, so in explaining something, your explanation should be shorter than what you're trying to explain.
Yes.
But part of what we typically use explanations in our models are not really only the explanation of that data, but they are backed up by much more data. So actually, if we weigh that complexity, we should divide, like if we add mass balance, and we use 20 lines of codes to implement mass balance in our model, we should divide that 20 lines of code by all the catchments and all the things where we applied it before, because we are also using it for that. So in terms of added complexity, maybe it's just 20 lines of code divided by 20 million cases where it helped predict. Right, so that's where it becomes difficult, like how much of the complexity in our model should we really count as part of the explanation, and certainly fitted parameter values are a clear example of things we should count, but maybe even that is only to a certain degree, because maybe we have prior knowledge about the distribution already. So in that case, only the description length relative to already having that distribution should be counted. So actually, if we have a very sharp prior knowledge, then the parameter values that agree with that prior knowledge should receive less complexity, because we would pick short codes if we code that prior knowledge on the parameters even there. So yeah, these are nice ways to think about it, like maybe all the things that count parameters as a measure of complexity, like archaic information criterion. They also don't consider like how much prior knowledge you already have on those parameters. So actually you should look maybe at some kind of divergence from a generally accepted prior distribution on parameters as being a measure of how much complexity you add. Yeah, so that's I think a key point where more research is needed. I'm actually not that hopeful that we actually can make it into a practically applicable tool anytime soon. I think the fact that we have such short data sets and our processes are so complicated, plus the fact that we have all this prior knowledge that we have to decide on whether we choose it's an accepted fact or whether we basically put it up for discussion and make it part of the complexity. But I think the recent developments in doing this large machine learning exercises over big data sets of many catchments maybe can tip it a bit in the direction where these things become more applicable. But I don't think it's very applicable in the one catchment comparing several simple models kind of setting.
Yeah.
Except for as a kind of fundamental background idea in which we can kind of interpret many existing approaches.
So I have no idea where this fits into this conversation, but something that Chris said made me think about, I started kind of thinking about models that you can find a simple way to go through a complex model. So I was thinking about model inputs. So you have 5 model inputs and they're like a basketball team. I must be getting excited about basketball season. So you have, these 5 guys, they're going into your model. Sometimes you need all 5 of them and they work together in a certain way and they make a play and they have your model output. But other times you have one player that goes and makes a slam dunk. So there's really only one input that triggers something in your complex model to get your output. And I was just kind of thinking about how you could have a complex model where you don't necessarily trigger all of the complexity within your model at the same time, or you could have an entire data set where you never see snow, so your whole snow module never comes into effect except for like one data point or something like that. And kind of like, what is that saying about? It's not saying that you shouldn't have that there, but it's just kind of like you never accessed it, and it's so dependent on your input data's ability to reach all the parts of your model.
Yeah, definitely. So I would say if that's the case, then you don't need the snow model if you only look at that data set and that's your only window on reality. But if you've seen other catchments and you know that snow exists and that it might happen, then you're actually having a lot more information than your model selection has, right? And so in hydrology, we're always kind of trying to merge data and our prior knowledge. And I think these large catchment studies are basically getting so much data that the prior knowledge starts to become unimportant at a certain point, because in the end, all our prior knowledge is also derived from data. Like we didn't come up with mass balance as an independent truth. It was derived from data. So I think the process of learning in itself is enough to find reality. But we have a lot of baggage in terms of both our evolution and our brains soaking up reality from our environment. So it's the question like whether the machine learning models that are only given a limited window on reality can outpace that by a stronger ability to learn, maybe. And so on the one hand, they have less data, but on the other hand, maybe they're not bound by our fundamental laziness in not wanting to do 20 million of the same computational steps. But yeah, that's maybe another point that And that's a big difference between Shannon's information theory and algorithmic information theory. Algorithmic information theory only refers to strings of data points. So it never makes a reference to an underlying probability distribution that the data came from. While in Shannon information theory, everything is tied to the distributions. We measure properties of distributions. But in a way, I find the algorithmic perspective more satisfying because the distributions are some kind of imagination of something behind what generated the data, and we make a step there while the data is real. And so maybe it's related to frequentism, where they say there's a real probability distribution and we just see samples of it. But you could also say, like, we have the data, and the probability distribution that we say generated the data is an abstraction, and actually the data is the only reality we have.
I'd actually like to respond to that. I'm not sure the data is more than an abstraction itself. The data are a representation of something. And I've been trying to think about how to pose this, but it's definitely outside the scope of what would be required from an algorithmic information theory. But you can measure something like streamflow in 100 different ways, and the measurements themselves might be reflecting on a simplification of a process. Like if you measure it from a satellite, the process that generates that streamflow with that sort of information might be simpler than if you measure it with a Doppler radar on the stream or something. And not that you can somehow try to squeeze that into a compression of a model, but I guess I'm just trying to comprehend the data string as the real world system versus it being an abstraction of the real world itself.
I'm not sure Jonathan, I'm not sure that anybody's saying is the data is the real thing itself, but implicit in your statement that you have different ways to measure streamflow was also the fact that you somehow, through other forms of observation, have determined that there is something called streamflow there, and then you're choosing to represent it.
That's right, yeah.
Using different ways, right? So my argument against the frequentism-Bayesian dichotomy is that whatever presumptions they make about priors, they both attempt to extract an explanation, and the very attempt to extract an explanation presumes something behind the data.
Yeah, so maybe in the algorithmic information theory framework, we can think of it very simply as we are fed a series of numbers, which are essentially certain bits in the computer, and we're trying to predict the next one, and we don't care about what it represents. And as long as we're independently of that happy with that the numbers that we have in our representation are useful to make some decision, like if we call it cubic meters per second streamflow, maybe streamflow in reality is the number of water molecules that pass a certain cross section. But then yeah, I guess maybe that also ties into reinforcement learning, where it's just about an agent in an environment, and it just tries to make decisions that optimize some objective function, but it doesn't care about whether there's deeper realities beyond what it observes, as long as well, I guess if there's still a decision to make about what to observe, then it becomes a different problem, right? But if the way we observe is fixed, then we can just optimize our actions based on whatever observations we have and what we think will happen next. Yeah, but any assumption about or any discussion about whether the representation is actually reflective of reality is based on having some other way of observing. So just the firing of the cells in our retina is also just data, and yeah, I guess I'll stop there. I'm never really good at making a concluding point, so.
Yeah, I guess I think to take that just a quick step further, if we are looking for the model that is the simplest representation of the data, I guess that's a decision. I think there's more decisions that need to go into the model itself than what can be defined through algorithmic information theory, and how to capture that additional information is what I'm kind of struggling with.
Yeah, I agree, because at the end the data are behind the data. It's multiple processing, not just in hydrology, anything, whatever discipline. So data, I agree also with Steven, because at the end the data is representation or a sample, and if you think more about that in terms of statistics, let's say it's sample from a population that you never observed. And also this data, actually a stream flow, and this is why we have different values, right? It's because of we are not accounting for different processes, and this is like multiple processes just mapping to a single time series. And there's a lot of information that we are losing, but not just how much information we are losing. We would like to link the amount of information that we are losing to the different processes. But again, for that, we need to at least decide at the beginning if we should include some process or not, right? It's like the example that Allison provided with the snow, and with the snow it could be very simple. But for example, for percolation, it's like do you have that process, or of course usually the process is there. So then is the point of how, if our data allow us to better infer any of those processes. And yeah, for hydrology, we usually have a lot of data, right? But if you try to think about that in general terms, so when going to the field, and you are in any part of the world, and you know about other parts of the world or other, planet, you cannot say, let's say we have the knowledge about what's there. Right? It's kind of the same as algorithmic complexity, I would argue.
Yeah, but in a way, like, let's assume you have a kid and that's the perfect learner. Then our role is basically to, like, we keep it blindfolded and then remove the blindfold at specific things that we decide. And the result of how much that perfect learner will learn, yeah, indeed, it depends on when we take off the blindfold and when we keep it on. But that doesn't mean that there's anything wrong with the perfect learner, right? So I agree from a practical perspective, those are also decisions, but like in an imaginary world where we have all the computational power to run these algorithms, we could just feed it all the data we have. And of course, with all the data we have, it includes anything that fires in our neurons. So then then there are not these decisions anymore with what we think is important to include in the data set, or what we think is reflective of reality, because our whole window of reality are only our observations, and any reference to something more to reality compared to our data set presumes that our data set is a limited subset of actually all the data we have. But yeah, that's of course all from the very theoretical perspective. So that's why I'm not too confident yet that I will directly apply algorithmic information theory to produce something directly useful in hydrology, but I think we can still use the concepts to kind of fine-tune the simplifications. So as soon as we realize that everything we do is some kind of simplification of the ultimate learning, then we can see which are the simplifications we make. So for example, instead of using all computable models, we always use a subset of models. And then we can think about whether, for example, these LSTMs, what part of the computational space are they missing? Probably not much from a practical perspective, but I guess they do not do partial recursion, so maybe any functions that use that cannot be perfectly converged to. Is that important in hydrology? Probably not. So that might be a good indication that type of model covers, at least for our practical purpose, the whole model space. Then the other question is, do we accurately account for complexity? That I don't understand that, because like it seems to me that these LSTMs use lots of parameters, but on the other hand, these matrices are sparse, so maybe there is they're given a lot of freedom, but actually they're not using all of it. But yeah, I know too little about it to really comment on that. But that's what I would like to understand better by talking to some of the guys and girls that are working on that.
All right. I think we have had a great discussion today, and I'm calling for the end of the session for today. I just want to thank Stephen for all the explanations and for expanding our knowledge of this paper. And to Allison and you that they needed to go, but thank you for moderating this session. And yeah, our recorded video will be uploaded to the YouTube channel, so you can check there again the whole session. And I'm calling also for one more volunteer for the next session. So if you want to contribute as a volunteer, please and sign up in the wish reading list that it's in our site. I'm gonna copy and paste here the spreadsheet location so you can volunteer. And I think that's all for today. Thank you, guys.
Okay, thank you.
Thank you.